this is the current dividend tool in parallel circuits. So here it is explained by this diagram as well, that we are having this current IA, and it is divided in I1 and I2. So I1 is R2 divided by R1 plus R2. Okay, now coming toward the KCL and learning its basics. So before knowing about KCL, let us define some basic quantities, entities. First of all, let us know about the node. Node is any point where two or more circuit elements are connected together. So if we are having this thing here, this is a node. The branch is a circuit element between two nodes. So let's say we are having this circuit. So this is a branch because it is between two nodes. It is between two nodes. This is a branch. This is a branch. This is a branch. So this is a branch. So any point, any 2 points gives us a branch if something is connected in between them. Okay, loop is formed from branches when the branches are closed. So if we check this circuit, in this circuit only one branching system is closed, so this is a one loop circuit. If we close this thing by a battery, we will have two loop circuit. It is not necessary that we use loop in a direct manner. We can also use loops in indirect method, but the rules of loop is that it should cover all branches. It should not overlap two times in a single loop, but it should cover all the branches. So if we want to loop this circuit, first method is that this is, let's say, loop 1 and this is, let's say, loop 2. You can give any direction to it. But the second method is that just cover all the branches. So let's say this is our loop 1 and this is our loop 2. So if we check this green line, it is also covering all branches. This branch is covered, this is covered, covered, and covered. So all branches are covered, hence this is also a valid loop structure. So loops must be equal whether you draw it directly or indirectly if all the branches are covered. So do remember this thing. Now let's solve this diagram with our previous knowledge that we have talked about. Here we want to calculate, we want to find that how many loops or branches are in this circuit. So here, if we just encircle this point and encircle this point and encircle this point, so we can clearly see that a node is a place where two or more than two components connect. So this is 1, 2, 3, 4 components are connected here. So this is our N1. Here they are also connected, so this is our N2. Here they are also connected, this connect with this, so this is our N3. So there are 3 nodes in it. Now coming towards loops, branches. So the connection between two nodes is a branch. So this is one node, this is other node, so this is a branch, one branch, B1. This is our branch, B2, B3, B4 and B5. So we are having 3 nodes and 5 branches. Now let us calculate the loops in it. Direct method will give us the number of loops. So let's draw it. This is our loop 1, loop 2 and loop 3. So 3 loops in it. Now let's check the solution of this thing. Here we are having these nodes and now these branches and these loops, and loops are the indirectly drawn, but it covers all the branches. So the first loop is covering this branch, second is covering this, and third is covering this, and covering these as well. So there is no repeated loops in it, and hence this loop structure is a valid structure. Now let us examine the Kirchhoff voltage law, because we are done with the looping system. Kirchhoff voltage law states that the voltage inside a loop is summed as 0. So if we add up all the voltages in this structure, we would say that Vs plus voltage across VR1 and voltage across R2 would be equal to 0. So summation of voltage would be equal to 0. So here is a thing that one must know. Try to add loops that makes the solution easier, not complex. So in the previous slide we saw that one was amalgamating the loop structure, but what if the same amalgamation makes our mathematics easier? So we should prefer a loop in which the bigger sources has emerging current arrows. So this will be very helpful if you see it in some problem solving. If a bigger voltage or current source is present and we use a loop for emerging current from its negative side, then we will have troubles in suggesting the signs of the drops. So one must use a current emerging from positive terminal of a bigger source. Okay, so this is the rule. Now here is the loop. In this loop the current is emerging from Vs, so Vs is equal to, now where are the drops? Rises is equal to drops. Rises plus drops is equal to 0. So rises is equal to drops but negative. So the drops are written in here as the loop current. So here the loop current is I, and now add up all the resistances, R1 plus R2. So this is our loop equation. So V is equal to I into this R plus this R, which is obvious because the total resistance is RT equal to R1 plus R2. Here they are using rises plus first drop plus second drop equal to 0, and then Vs is equal to I R1 plus R2. What we are using, we are saying that rise is equal to drop, so Vs is equal to I R1 plus I R2. So in both cases the thing comes to this singular equation, so we are good to go. You can study more about this law at this link. Okay, now here is a problem that is solved using the same law. In this problem we are verifying that KVL holds. So we are having a 12 volt source and the current of 0.2 ampere is flowing in it. So we'll calculate the drop across this and this and this, and then subtract it from this, and we should get V1 plus V2 plus V3, or Vs minus this thing equal to 0. So check this example. You will have to calculate the voltages. So voltage can be calculated as this voltage and this voltage and this voltage, and then subtract it from here. So just go through it through yourself. The main objective of KVL is to find the unknown currents first. Unknown currents first. So KVL is used for calculating unknown currents. So let's calculate some currents in the example. Okay, so these are some of the examples which we will study and calculate our matrices for I. Further we can solve those matrices. Okay, so we are having this universal rule, and let's read this out loud. While drawing a loop, the arrow of the direction of the arrow tells us about the sign we are using with the voltage or the current source. So if we are using this arrow emerging from this side, this will tell us that what should be the rise voltage, the voltage rise sign. If it is from this side, then we will say that it is 18 equal to I1 into this plus this plus this. If we say that the direction is like this, so it is going inside this, so this is, let's say, I2, so we will say that minus 12 is equal to I2 into this plus this plus this. So we will study these things later on. The drops are always negative for resistor, capacitor, and inductor if we use the drops and rises on the same side. So rises minus drops would be equal to 0, so we will always have negative drops for these components. So I will not use this method because the second one is easier. Rises is equal to drops. Okay, now let's solve this circuit for I1 and I2. We will use our own loops, the loops of our choice. So let's have one loop like this. So this is our I1. So this is our I1, and let's say this is our I2. So one is clockwise, the other is anti-clockwise. Now for I1 loop, 18 is equal to I1 multiplied by, I1 is going through this and this and this, 1 plus 6 plus 2. So 18 is equal to I, 1 plus 6 is 7 plus 9. Okay, and in the same circuit we are having this singular resistance in which I2 is also flowing. So this loop is having rises due to this thing and drops due to I1 as well as I2. So we can say that plus I2. Why plus I2? Because I1 direction and I2 direction are same. So plus I2 into how much resistance it is flowing through? 6. So plus I2 into 6. So this is our loop 1's equation. Now let's write the equation for loop 2. Let me erase these components and just write the loops that I have used here. So one loop was this and other loop was this. This pencil tool is quite nice. Okay. So for this loop, let us consider the same rules. So emerging current is from 12 volt. So 12 is equal to, now it is for loop 2. So I2 into 3 plus 6 plus 4. 3 plus 6 plus 4 into I2. And the same 6 ohm resistance is common to I1 as well, in which I1 is also dropping some voltage. So plus I1 into 6. So we got this equation: 12 is equal to 6 I1 plus 9 plus 4, 13 I2. So we are having let me delete this thing. Okay.